A big thing in manufacturing and any industry actually, or any business, is statistical process control. It's used in healthcare, finance, things like that. So this is actually a good one to learn. This is right up there with NPV and IRR. Okay, let's spend some time on this slide. Let's say I go off and start buying apples at Walmart or something, right? I start weighing them. Well, I'll come in, here's this apple, get another one, here's this apple. These are the weights, right? Keep on going. Well, eventually, if I weigh enough apples, I'll find a lot of them are right there around the average. That's that X bar on the bottom, right there on the average. But they will vary a little bit, right? Well, those variations will get smaller and smaller, right? These are what are called standard deviations. So about 99.7% of everything will be within plus or minus 3 standard deviations. And I've got a video, I'll link it to you. They'll explain what a standard deviation is. There's a lot more to it than what I'm going to present, but for the purpose of this course, it should be good. Well, it turns out that the closer you get to the center, the more and more apples you're going to find, right? So the standard deviation, and explained in the video, turns out that 68% of everything we measure will be within plus or minus 1 standard deviation. 2 standard deviations will have 95% of whatever it is we're measuring, and 3 standard deviations, 99.73%, darn near all of them. So what we're going to do then is we're going to use this, and we're going to see if something varies outside the normal. You can figure out probability, things like that. And that's what statistical process control does. Let me know if this video doesn't start automatically. I'll also copy this link in the email I send you. Okay, here's that the normal curve, the standard deviations and all that. All I've done is we turn it upside or on its side here, right? So my average, I still got my 3 standard deviations. I just turn it up on its side. That's all I've done. Okay, I'm going to go out 3 standard deviations. Going up, that's my upper control limit. Go down, that's my lower control limit. And that's plus or minus 3 standard deviations from the average. Again, the average weight of the apples. Now watch this slide. I'm going to start off with my average, go up to my upper control limit, my lower control limit, have an element of time, right? And then I'm just going to start measuring points as I weigh the apples. Where do they lie in its weight? And I'm just going to go out. So it's the same thing as I did before, except I'm stretching it out over time. Now, if I were to take this thing after I get all done, tip it back over to the shape of it, all those little points will fall down and make that normal curve, a nice bell-shaped curve. So where do we use this thing, right? In the manufacturing environment, it'd be in quality control, right? This was first developed in about 1924, I think, by a guy named Walter Seward, who worked up in Chicago for Bell Labs. And he understood that all things vary. So what he did is he said, I'm going to manage that variation, try to control the variation. Well, it was used in manufacturing a long time ago. In fact, this is what the Japanese used in the 1950s to get better and better and better. American car industries kind of ignored it for a while. But now it's gaining popularity in all business. It's a lot of healthcare, actually, is a big one. So the control chart's the big thing on this. And now I'm going to send you a link, and we're going to play with that a bit. But What it does just like we had before, combines the data, but it puts it out over time so it can see trends and changes and variation over time. Huge, actually huge. Okay, this is a control chart example. Again, I'm going to send you a link to download one. But this allows determination of systems controls. By in control, we mean it's not varying more than plus or minus 3 standard deviations, or doing some other things that are funny, right? So what they do is they make these charts, and these charts tell us a lot, right? And there are two types of variation. There's the common variation, which is basically just random variation. And then you got special cause variation. Special cause is which data can't be assigned to, or which data can find a specific cause. So you can go into the process and say, oh, this is what's causing it to vary so much, right? Or this is what causes one point to be out of control. It might not be good. It might be an accident or whatever, but it allows you to fix processes. Not the product, but the processes, so you make a good product. So look at the two examples. You got common cause. Looks pretty random, right? All within the control limits. And on the bottom one, you got special cause variation. They go outside the control limits. Something's going on in that chart. This is actually one from a hospital. They were having a lot of readmission rates, readmissions. So in other words, they discharge a patient, he comes right back, right? And you can see they're about almost 20%. So they started doing SPC on the readmission rate, and they calculated their standard deviations, their control limits, and then they started doing SPC, and they started making changes, see if they could make this thing come down. That was the whole point of this. And if they did make a change, what effect did it have on the readmission rate? There are a lot of different types of control charts. We're just going to work on the one type, the variable and continuous data. But there are a whole lot out there. Depends on what kind of data you have. So why would we use these things? Well, you can see if there's really true change or random noise. Think about somebody driving down the road. You know, we all sway a little bit, right? But you see those people that'll sway a little bit and they'll overreact. They're reacting to random variation, basically. Too much, actually. Where if you make a hard turn and fall off the shoulder, well, that's a special cause, right? So we don't want to just chase random variation too much. We want to hit the meaningful changes, the things that are important. So an SPC chart lets us see that. You can see trends. We can see how much it varies, and also measures how much of an impact we made if we try to change the system. So SPC is applicable to any process, because what it does, it reduces variation to a reliable process. So even if you're doing bookkeeping, right, you can count the number of mistakes or something like that. Any process can benefit from SPC. Most often it's used in quality improvement and in management too. If it's a well-managed company, they'll be using these things too. And it's very easy to interpret, right? And this guy, Benningen, said statistical process control is a branch of statistics that combines rigorous time series analysis methods with graphical representation of data. It yields insights and quickly find a way of understanding delay decision makers. So what he's saying here is we can look at trends, we can look at data, we can look at variation. It's a snapshot for us, any process. So what do we do here? Well, it establishes what random noise variation. So basically when they mean a stable period, they're talking about a process where you're not fooling around with the controls or anything. You're just letting it run, right? You can see how much it varies just in the absence of fooling around. That's your random variation of the process. And then if you introduce some kind of intervention, try to improve it or something, you can see if it's been meaningful or if it's just random noise again. It's very powerful for process improvement. Very powerful. So what are the key steps? Well, first of all, you say, what process do I need to control? And then how am I going to measure this thing? And you're going to select the appropriate control chart. For this class, it'll just be this chart I give you, the Excel spreadsheet. And then you generate that chart, and it'll compute automatically the mean value and also your control limits. And then you can observe the variable patterns of the patterns and see if you need to do something with that process. And the deviation from the variation, it could go more than just being outside 3 standard deviations. So there are a bunch of rules with this. We used to have to do it by hand, manually, but now the computer does it for us. But go ahead and take a look and see what they are. Okay, here are the examples. If you look at one, it's outside the control limit. That's an obviously out of control. You got 6 in a row, either increasing or decreasing. That's a trend. Random variation doesn't follow that pattern. It's just random. This is something's going on there. Number 3, 4 out of the 5 successive points are more than 1 standard deviation. Doesn't happen very often by random chance. All these are about a 1 in 400 chance. And they got 2 out of 3 beyond 2 standard deviations on the same side, right? All these are not random events. Something's going on. So how do you use these things? One, well, you just monitor the process. You got random variation, no special cause. Man, that's a good process. Don't do anything. You can identify things that you're doing, inputs and things like, I don't know, something simple as a new tool or a change in RPM, something like that, to the outcome. Are you getting the results you want? Differences between groups. I mean, first shift is different than second shift or suppliers or whatever. And it's self-management intervention. So you can monitor changes in like the individual machines, the suppliers, anything at all. That's a process. All right. And it also determines lag time. Okay, I'm going to implement this change. Let's see what happens. Oh, it took a couple weeks after that, right? Right now we're in a pandemic as I record this. So how long between exposure and you start feeling symptoms? It'd be kind of something like that. Okay, this is another one I used at a hospital when I was doing some consulting there. Basically, they're looking at customer satisfaction, right? So what they did is they started recording the results of these feedback cards. And they did some changes, and all of a sudden they see a shift in the process. And with the SPC chart, you can tell that the process change was real. You actually got some points out of control on the good side, right? And they got better. This came from a factory. They used to make a lot of toxic waste, and it was tough to dispose of. So what they did is they said, all right, we're going to try to reduce the amount of waste we produce. So what they did then is they had the baseline from SPC. Again, you can see it's just random variation. They implement some changes, and it went down again in a good way. We got random variation again, right? So, okay, so what are some of the limitations? Well, you got to have a lot of measurements. The more the merrier, right? But it has to be done over time, right? It has to have some degree of autocorrelation. In other words, what they're saying here, you got to have some things in between the measurement and what's happening, what you're doing to the machine, process, or whatever, what's it doing on the output. There are some cases where this thing can't be used, but I can't think of any. And the example I could find is a seasonal variability, like on a farm or something. And if you don't really understand the whole thing about control charts, they're not going to be very useful. That's why you have to have somebody come in usually to do the initial use, sit there and just teach it and coach and get this thing running. Otherwise, it will fall flat on its face usually. Get back in touch with me if you have any questions. And again, I'm going to give you a spreadsheet. I'll do this automatically, and I'll also record a video. Kind of explains how that spreadsheet works, and then we'll do an exercise. By we, I mean you. With this open book, open notes, but you'll do an exercise.